Hello.
Good evening, everyone. Now we move on to session 13 of our faculty development program. Steel is the backbone of industrial progress, but its sustainability is now under global scrutiny. To discuss the future of green and clean steel, we are honored to have Mr. Abhik Roy Chowdhury, who will deliver the session on topic the green, clean and future steel. Mr. Abhik Roy Chaudhary earned his BE in Mechanical Engineering from Bengal Engineering College, Shivpur, and later obtained Masters in Mechanical Engineering from Jadavpur University. Midway through his career, he studied at the University of British Columbia in Vancouver, Canada, earning double master's degree in metal and material science and computer systems. For most of his career, he has worked with Tata Steel Automation Division, where he specialized in process automation. The blast furnace process models he designed and developed are used across all Tata Steel blast furnace and its subsidiary plants. The models have reduced coke consumption by 2 to 5 kg per ton of hot metals produced and have significantly decreased the emission of exhaust gases. As a result, the company earned carbon credits. Additionally, he has led several process automation projects such as the dynamic secondary cooling system at casters, the cooking control system, the combustion control system for pellet induration furnace, as well as project in sintering, batch annealing furnaces, and others. He joined MS Fox Solutions as Vice President of Technology after retiring from Tata Steels, where he developed the combustion control system level 2 automation for the reheating furnace at the Tata Steel Thailand plant. This system reduced fuel consumption by 5 to 8% and significantly improved the decarbonization of waste gases. As a principal consultant at Lotus Wireless Private Limited, he developed the blast furnace process model for the Bhilai and Durgapur steel plants. They are currently undergoing tests and trials before becoming operational. He owns multiple patents and copyrights in this specialized field. He has been recognized as a champion of Aspire project, especially on fuel reductions. He has also received the Tata Innovista Award for innovations and was a candidate for Tata Steel's Technological Leadership Program. He visited MIT, the University of Science and Technology in Beijing, the Center of Research for Metallurgy in Ghent, Belgium, the Max Planck Institute in Germany, and various steel plants in Britain and the Netherlands. We are truly privileged to have him with us today, and we eagerly look forward to his lecture on the green, clean, and future steel. We extend a very warm welcome to you, sir, and request you to take us through your expert lecture. Over to you, sir.
Thank you very much. Am I audible? This is the first thing which I want to say. Am I audible?
Yes, sir, you are audible.
Okay. Can I start now?
Yes, sir. Yes, sir.
Okay. The topic is that emerging frontliner. It's a theme, emerging frontliner in energy, climate, and sustainability. And my topic is that sustainability in the steel plant with a clean and green steel, and what will be the future steel in future, what may come in. So welcome to this session on the forefront of sustainable steel productions. Today we'll delve into the definition of clean and green steel, its environmental impact, emerging decarbonization technologies, policy frameworks, and the pivotal role of academics here, which is very important in this transformation. We will also conclude with a question answer session. So once again, thank you very much, my audience. And let me proceed with what I have today and what I can deliver. It's an interactive. You may, anytime you may ask me the questions. If possible, I'll give the answer, or else I may come back to you later on. The first thing is that we must know what is clean and green steel. And as we all know about it, clean and green steel refers to steel produced with dramatically lower greenhouse gas emissions. This is achieved this is achieved by replacing fossil fuels in production with clean energy sources, primarily through the use of renewable electricity, green hydrogen, and innovative processes instead of coal in iron making. Traditional steel making using blast furnaces emits approximately 1.8 to 2 tons of carbon dioxide per ton of steel, which is huge. Green steel aims for near zero emissions. They want to get it, commit or reduce it to almost zero. Primary releasing water vapor from hydrogen use or capturing CO2 before it enters the atmosphere. The term green underscores its alignment with global climate goals, signifying steel production with a minimal carbon footprint. The iron and steel sector accounts for 7 to 8% of global carbon emissions, more than any other heavy industry, primarily due to its dependence on coal in blast furnaces. Now, about hello, am I audible?
Yes, sir, you are audible.
Yeah. Okay. Now, about 75% of steel is made in coal-fired blast furnace. The steel which is being produced out of this, the total steel plants, 75% they use the blast furnace route, and each requiring intense energy, heating above 1000 degrees centigrade and releasing large amount of CO2. With global steel productions reaching 2 billion tons in 2020, which has already reached, and its demands and the impact of the large amount of CO2 is very high. Now, the climate goal to meet the Paris Agreement, quite recently there is a Paris Agreement, the steel emissions must fall. This is the climate goal of the entire the global goal. The steel emissions must fall 50% by 2050, which means that carbon dioxide which is being emitted from the steel plants as of now should fall by 50% by 2050. That is the target which has been given by the global climate missions. If you see the graph on the right side, you'll see that the different curves and how the carbon dioxide is increasing since 1990. 1990 to 2014, this is the graph over there. You will find the maximum carbon dioxide is being emitted by the China steels. And definitely, China is having almost 1,000 metric tons of steels, million tons of steels. In respect to that, India is also increasing. India is also increasing its emission, and it is around 2,000 million tons as of now. Well, as of now means it is a 2014. That means it is by 2025 it must be more. But on the other hand, if you see the US and Europe, they have already taken actions, and then gradually there is a gradual declination of the carbon dioxide from their steel plants. So the main culprit as of now we can see is China is definitely very high, but India is also not that very far. It is also increasing. So it is it's alarming. Now let's come to the next slide. The next slide is again it's a little bit of repetition. Global carbon dioxide emission, according to the World Steel Association, 1.88 billion tons of steel were produced globally in 2020, resulting in the 22 billion tons of carbon dioxide. That is the figure. And from where this carbon dioxide is coming up? It is coming up from the blast furnace and basic oxygen furnace route. How much is it? 73%. Then electric arc furnace, it's another route. It is a 26% and the remaining 0.5%. Okay. The share, how much is it means that in the steel plants, that amount of carbon dioxide is being emitted. The most of the emissions are coming from the blast furnace BOF route. And most of the 75% of the steel plants use this blast furnace BF route. Okay. Then comes the electric arc furnace. This is the steel, another route of steel making, which covers 25-26% of the steel plants, and which is also emitting the carbon dioxide. But as you can see, the blast furnace BF route is the main culprit. Okay. Now coming to the blast furnace BF route in the rightmost part, this BF BOF technology uses coke to produce heat and as a reducing agent turns iron ore into metallic iron. So BF BOF demands 8% of global energy, emits 7 to 9% of global CO2 emission. I'm repeating that. BF BOF route that emits almost 10% of global CO2 emission. BF BOF routes requires 800 kg of coke to produce 1 ton of steel. It requires 800 kg of coke to produce 1 ton of steel. And it emits almost 2 tons of CO2, the carbon dioxide, per ton of steel. Okay. Now, if you want to move forward and if you want to see that how this can be deduced, then we must know that what is BF. Any question? Any question so far? Okay. What is BOF route? What is EAF? And then we'll go forward how this can be replaced. This coke and coal can be replaced by the hydrogen. This is the blast furnace. On the left-hand side, you can see this blast furnace, and there's the stoves, hot air stoves. In the stoves, that air is being heated up, and it is being pushed into the blast furnace. And what is happening in the blast furnace? It basically, blast furnace operates on the principle of chemical reactions, whereby carbon monoxide converts iron oxide to elemental iron. Okay, I'm repeating it. Blast furnace operate on the principle of chemical reductions, where carbon monoxide converts iron oxides to iron, elemental iron. It converts iron ore into molten pig iron by charging iron ore and coke from fuel and limestone into the top of the tall vertical furnace. So hot air is then blasted into the furnace, causing the coke to burn and create carbon monoxide, which ascends. It's a gas, so it ascends to reduce the iron oxides, which is actually descending from the top into the molten iron. Limestone reacts with the impurities to form a liquid slag, which floats on the molten metal. The molten iron and slag are tapped from the bottom with the hot gas exiting the top. The hot gas which is exiting the top, that is having a carbon dioxide. That is what we are talking about, how to reduce that exit carbon dioxide. What are the benefits of the blast furnace? It's a large scale, cost effective production of molten iron for steel making, high efficiency and product consistency for downstream processes, very mature, very old technology, proven technology for bulk metal production. It serves as a source of energy, that hot air, which is the hot blast, which is exiting from the blast furnace. It itself is carrying that energy like the carbon monoxide, which can be used as a fuel. So it serves as a source of energy from the waste gases, and it provides opportunity from the byproducts like slag. Now the slag, which is the impurity on the iron, which is being kept out, it actually goes to the cement plant and the cement is made. So this is the utility which we are getting, byproduct utility which we are getting from the blast furnace. So in 1 second, just repeating that iron ore and the coke, they are mixed together and they are put in on top of the blast furnace, and the hot air is being pushed from the bottom. Now the hot air react with the coke, become the carbon monoxide and carbon dioxide, and then extract that iron from the iron oxide. And that extract the iron which has been extracted is in a hot metal, in a pig iron hot metal. It has been collected in the hearth, and the hot gas which goes upwards, it includes the carbon monoxide, very rich carbon monoxide and very rich carbon dioxide. The carbon monoxide is a fuel. It can be used for two other furnaces as a fuel. But carbon dioxide is a waste gas and it is polluting the air. And as we have discussed earlier, that it is almost 2 tons, almost 2 tons of carbon dioxide is produced for 1 ton of hot metal being produced. Okay. Coming to the next slide, it is just that the reduction equations. And if we see the reduction equations, then you see that on the right hand side, it is generating CO2. And that is the reason why I put that reduction equations over there. The all possible that Fe2O3 is a hematite, is the iron ore. Fe3O4 is a magnetite, it's an iron ore. FeO is a woodstite, it's an iron ore. These iron ore are being reduced by the carbon monoxide, and the carbon dioxide is produced, which is a waste gas, which is our topic today, and which is actually polluting, which is not green, right? Which is not clean, which is not green, right? And this iron, Fe, it is in a liquid form. It is collected in the bottom, and then it is a molten iron. Then it is some iron. It's a pig iron. Is having a high level of carbon, which is of saturated percent of 4 to 5%, which goes to the steel making shop and it's converted to the steel. So this iron has been produced in the iron making shop. Now it goes to the steel plant, steel making shop. It's a basic oxygen furnace process which converts molten pig iron, which has been collected from the blast furnace, and steel scraps into steel by blowing high purity oxygen. What is happening over here? That pig iron which is coming from the blast furnace, it is being poured into this molten bath, and also some of the scraps, the recycled scraps are all poured into it, and then highly pure oxygen of around 98% and 99% of pure oxygen, it is being launched into it. It is launched into it, and it starts that molten bath. And what is happening, you can see the reactions in the right hand side. That's the carbon is now getting oxidized. In the blast furnace is all reduction equations, all reduction from the oxides to iron. And in the steel making shop, it is that the impurities are being converted in the oxides form. Like carbon is oxide and become carbon dioxide again. This carbon dioxide is going up, which is also polluting the air, which is not green, which we have to reduce, which is our topic. And the other is the slags. That yellow part you can see is the slag, this steel slag, metal slag. They're like calcium carbide, calcium carbonate, P2O5. Uh, these slags are basically removed, and the steel which is there, steel actually is put into it goes to the mills where they cool it, they put it, they convert it into slabs, and they make the coils, and the coils go into the market, and then you can see in the market like the automobiles, the cars, like the fabrications, like the flats, the the rods, all possible things are being formed from this steel, and which go to the market and been put it over there. Everything is fine. Here the benefit is that it's a high speed production. Like within an hour, it produces steel, and it's a very precise control over the steel composition. Steel composition is very important. Like in a car, the steel composition should be different, but the steel which is being used in the offshore, in the underneath the ocean, steel which is being in the weapons, steel which is being in the fabrication or in the infrastructure building are of different composition, and these compositions are can be controlled in this bath. Fine. So everything is fine, but on the other hand, we are getting that carbon dioxide again, and this carbon dioxide is going into the air as a waste and it's polluting the air. Now, this is a picture of the entire steel plant, where it is just simply showing that how the carbon dioxide are as a waste gas are coming to the atmosphere from different plants. I do not want to elaborate. You can see the blast furnace in the middle, which basically produce at least 1200 kg of carbon dioxide per unit of hot metal, unit of 1 ton of hot metal, and this is the maximum one. But the sinter plant, the coke plant, the hot strip mill, the steel plant, the lime plant, they are also producing or emitting that carbon dioxide to the atmosphere. So in totality, what we can see, the total CO2 emission is 1,815 or almost 2,000 kg of carbon dioxide is produced per ton of rolled coil. That whatever steel plant they are rolling, for each ton of steel, each ton of rolled coil, what we see in the market, the rolled coil, they have already produced two tons or 2,000 kgs of carbon dioxide, which is being mixed in the atmosphere, which is going into the atmosphere. Just simply, we cannot do anything with that. It is a waste, absolutely waste. It's just nothing but the pollution. Correct? So what to do? So much of carbon dioxide is being produced. If we want to produce steel, we cannot do anything else till now. Now, I must, before we go to the remedy, there is another process which is also very important, but it is not as popular as blast furnace. But this process is called the direct reduction process. The direct reduction process, it refers to solid state process, which reduce iron oxides to metallic iron at temperature below the melting point. Like it is a direct reduction. The iron ore which is being put into the vertical shaft from the top, it is reduced in almost below the melting point of the iron. That is, it is reduced and it is not being melted to a liquid pool, right? And how it is being reduced? It is reduced by the carbon monoxide gas. It is reduced by the natural gas. So the natural gas and the carbon monoxide gas are being pushed into that vertical shaft from the bottom, even from the middle side, and from the top. This iron ore are charged. And they are all reducing gas, so they reduces that iron oxide and extract the iron from the iron oxide, and they become the carbon dioxide, and then again carbon dioxide goes to the atmosphere as a waste gas. Now, if you see the underneath, there is a typical uh, uh, typical picture photo of the production of the direct reduction furnace. This you can see it's like a briquette. It's a small sort of pellets, which is absolutely pure pig iron, and this pig iron, these small briquettes and irons are then put it in the electric arc furnace to convert it to steel. So there is a conversion. First, you have to make that iron. Iron is an impure steel. It is not a pure steel. Iron is having at least 4 to 5% of carbon. But when you are making steel from iron to steel, then this carbon percentage should have to be reduced to at least in the range of 0.8, 0.5, 0.6, 0.1. In fact, less than 0.1 in some typical steels, stainless steels. It's around less than 0.1, and at the most maximum 0.25% of carbon. So first you have to reduce the carbon from this iron to make the steels, right? Now, here what you can see that it is energy efficient alternative traditional blast furnace, and it is used in the electric arc furnace. Here, the carbon dioxide is not being much produced in the direct reduction furnace compared to the blast furnace. We cannot we cannot skip this electric arc furnace, because as I said, if there is iron making, it should be followed by the steel making. So what is happening that this electric arc furnace, a secondary steel making process that uses recycled steel scrap, sponge iron, and pig iron, that is from the DRI. And then there are the electrodes, electric arc, which simply with a high temperature, this EF process melts scrap steel and other iron-rich materials using high-powered electric arcs from graphite electrodes to produce liquid steel. After charging the furnace with the raw materials, the electrodes are lowered to strike an electric arc, generating extreme heat to melt the metal. Fluxes such as limestone are added to form a protective slag layer. Once melted, the liquid steel is refined and then tapped into the ladle for casting a desired shape. The benefits is that a sustainable method of production compared to primary methods such as the blast furnace, as it reduces the need for raw materials like iron ore and coke. Here is the benefit. Here in this steel making, we are not using that iron ore, neither we are using the coke. Coke is a carbon, and carbon actually produces the carbon dioxide. So massive carbon dioxide is not being produced in the DRI EAF route. So this reduces the carbon dioxide emission. But on the other hand, this is very much limited. It is in small scale. It is not being produced, not producing the steel, iron and steel in a larger scale. Okay. So nearly 25% of the global steel is produced from the EAF process. Now, here is a diagram which is showing that carbon dioxide, which is per ton of steel, which is being produced by different process of the steel making. Okay. So there are different routes. First is that BF, BOF, which we described, which is a standard and general. If you go to any steel plant, integrated steel plant, you'll find that BF, BOF route. This is, as I said, it's almost 2 tons of carbon dioxide they produce. Then the BF, BOF route, where coke is not, instead of coke, they are using natural gas. Then this DRI route, DRI-EF, they are also emitting the carbon dioxide, but not up to the level that we are getting from the BF route. Now, this DRI-DF route, if you keep on seeing it, that of different process and DRI-DF route, it is possible to reduce the carbon dioxide. And finally, when we are going to the hybrid, we are not finding that emission of the carbon dioxide. This is what we will be discussing now after this slide. That hybrid is basically it is how that carbon dioxide or carbon monoxide or carbon is basically being replaced by the hydrogen. That is the aim. That is the target of the global target, and that is actually that is the scope. There's a scope of research and scope of study in this particular field, that how hydrogen can replace the carbon. The carbon comes from the coal, carbon comes from the coke, and how is it possible to replace it? Okay, so the next slide. The next slide is it is a global meeting. Global meeting, COP26, 40 countries launched the Glasgow Breakthrough for Steel. Glasgow Breakthrough for Steel, aiming for near zero emission steel. Near zero emission steel. That is near zero CO2 emission from the steel. That is the target. That is the target, global target. To be preferred choice globally by 2030. That is the target. By 2030, there's a global target is at least 90% emission reduction should have to be there. How is it possible to do it? It's for it. The initiatives are driving R&D at a faster pace. This is why it is written in the bold statement, because it's academics which is in the audience, and it is for them to do the research work and to study in this particular area, that how is it possible to reduce carbon dioxide and make steel more cleaner, more greener, and that is the future steel. So blast furnace may go off, and blast furnace will be replaced by something else. So that's what we will discuss now. This global momentum that demands updated curriculum, again for the academics, updated curriculum and research from educators. Terms such as green hydrogen DRI. So let us study now, let us discuss on the green hydrogen DRI. Electrolysis steel are now crucial to industry vocabulary. This program will equip you with essential knowledge and examples to integrate into your teaching and research endeavors. My next slide is, so before I move to this hydrogen area, is there any question from the audience which I can make any answer? Okay. We'll go to the next slide. Is there any topic which I should go back and repeat it? Okay. The first thing is that environment impact. So if you reduce CO2, what will happen? Eliminate billions and tons of carbon dioxide, and carbon dioxide reduce air pollution. Okay. China is producing 50% of all steel, needs green steel for carbon neutrality. China needs more. I have shown you the graph. Energy and resource impact. If we do that, if we use hydrogen, if we replace the carbon, particularly the coal, by hydrogen, then what we need? requires significant clean energy. For example, Europe needs 400 trillion watt-hour of renewable electricity to produce hydrogen. Immense. By 2050, creates demand for renewable infrastructure and hydrogen production. So hydrogen production should have to be there. Otherwise, how do I get the hydrogen? How do we get the hydrogen? Then economic and industrial benefit. So new chapter, new chapter, new work. What will have opens new market with premium fossil-free steel. Okay. Early leadership offers competitive edge and creates new job opportunities in the fields like hydrogen and CCUs. I'll come to the CCUs, while avoiding carbon tariffs. Okay. So there is a discussion point beyond CO2 reduction. What broader social benefits can be anticipated from a global shift to green steel production? Repeating it, yes, beyond CO2 reduction, what broader social benefits can we anticipate from a global shift to green steel production? I'll go to the next slide. This is hydrogen-based direct reduction H2 DRI process. So we have learned that DRI process, direct reduction in product process, where the iron ore is being pushed from the top and the natural gas or the coal gas is being pushed from the bottom, and there is a reaction in between the coal gas, CO gas, C, and the iron ore, and it extracts the iron from the iron ore, and it is formed in a briquette and small pellets sort of things, and it is not at a very much high temperatures. Almost it's a lower temperature, and since the reducing gas is the carbon monoxide, and natural gas is also consists of carbon monoxide and carbon dioxide. So waste gas, the gas which will exit from the DRI, direct reduction iron, it includes that carbon dioxide, which is a waste gas, which is actually polluting the atmosphere. Now, the point is that is it possible to replace that natural gas? Is it possible to replace the carbon coke and coal gas by only hydrogen gas, right? So what is the process? Iron ore is heated in a shaft furnace where hydrogen reacts with iron oxide, forming metallic iron and H2O. I'll come in the next slide. I'll show the equation, and that then you'll be understanding that how the hydrogen and the carbon, the C, they are, both of them are very efficient reducing agents to the iron oxides. Okay, when the carbon reacts with the iron oxide, it produces carbon dioxide and the iron. When hydrogen reacts with the iron oxide, it produces steam and iron. So there is a difference. The carbon produces carbon dioxide, which is a waste, and hydrogen produces steam, which is useful, which is harmless, right? Okay. The current status, what is the current status? The people have just seen, right? I think by 2000, after 2010, 14, or 2020, the people in different global area, they have started experimenting with this hydrogen-based steel making, hydrogen-based iron making production, right? So what is the current status? Gas-based DRI exists 100% hydrogen. 100% hydrogen DRI is emerging. In some cases, they are mixing that hydrogen with the carbon gases, or the coal gases. Okay. The pilot project like Hybrid in Sweden have successfully produced iron with H2 since 2020, with commercial production planned by 2026. It is important to note that they have not yet producing that steel commercially. They are planning to produce it by 2026. but they are using hydrogen instead of the coal. Some opportunities and some challenges. Opportunities, yes, it cuts 95% of CO2 because it is not producing any carbon dioxide emission if using green hydrogen. Leverages proven DRI furnace design. Companies like SAB, Hybrid plan full blast furnace replacement by 2030. Strong momentum with 96 million tons per year announced capacity by 2030. These are the opportunities, but challenges. Challenges is that hydrogen supply is the biggest hurdle. 1 ton of DRI via H2 needs 50 to 60 kg of hydrogen, requiring 2.5 to 3 megawatt hour of renewable electricity. Massive power needs and electrolyzer deployment. Cost of green hydrogen is high, very high. Okay. Metallurgical adjustment and hydrogen embrittlement is also there. So it is not that it is a very easy task, but there are certain challenges. If you use hydrogen, then some challenges also we have to face, which we are not facing with the carbon with the coal and coke route. That is blast furnace and BF route. Okay. So discussion point, again, you can take it home. Give the massive electricity demand for green hydrogen production. How can grid infrastructure and renewable energy deployment scale effectively to meet future green steel needs? That means grid infrastructure, renewable energy deployment is another new chapter which will open up if you want to use the hydrogen instead of the coal. I'll go to the next slide. Here comes the equation, and here is a typical schematic diagram of a hydrogen DRI. It's like the similar DRI, and only thing is that it is instead of coal, it is coal and coal gas. It is the hydrogen is being charged over here. So hydrogen and iron ore they react, and hydrogen reduces the iron ore, and iron ore reduces the iron ore, and iron becoming the iron pig irons, which is then go to the EAF for the steel making. Okay. Now here's an important part. Very important part is if you see the equation, and the equation is that FeO, which is the iron oxide, it reacts with the hydrogen and it's become Fe and the hydrogen and the water steam. Okay, but and when you are using the carbon gas, coal gas, that FeO plus 3CO is Fe plus CO2. This is the difference. One is producing steam as a byproduct, as the oxide. Other is producing carbon dioxide after extracting that iron. But there is another catch, another area where we have to also look into it. That in this process, in the hydrogen process, it is highly endothermic. It is highly endothermic. I'm repeating it. That is, it cools the environment. Okay, which is not good. Whereas in the BF-BOF route, the coal gas, it is an exothermic. If you see the del H is minus 36.79 kilojoules, whereas in the del H in the hydrogen route, it is plus 62.44 kilojoules, which means it is absorbing heat. It needs heat from the atmosphere. It is endothermic, and then only it can extract iron and then produce the water steam. Okay, so this is a very important point. Now, key features, as we know very well, use of fossil-free energy in its entire value chain. That is, there is no coke, no coal. It is only hydrogen. The only carbon footprint comes from the graphite electrodes and the pure carbon added in the EAF. So EAF is the area where the electrodes are being used, and the electrodes are the graphite electrodes. That is the carbon electrodes. So that's what I'm saying, that only carbon present in that entire process is the graphite electrode in the EAF. Okay, so the any carbon dioxide that emits from this process is that which comes out from the graphite electrodes, if there is any. Okay, otherwise there is no trace of carbon dioxide in the process. It's only hydrogen. Okay, but I'll come to the next one. The next one is basically the challenges. Yeah, if you use the hydrogen, it's not that easy. You have to face the challenges. What are the challenges? One after another, we can go through it. The first challenge is that getting the hydrogen. Okay, the a plant of a with a capacity of 1 metric ton of steel will require 100 kilotons of hydrogen, equivalent to almost 12 tons of hydrogen per hour. 12 tons of hydrogen per hour, or 140 normal meter cube of hydrogen. It's a gas. 140 normal meter of hydrogen per hour. In order to get that 12 tons of hydrogen per hour, or 140, 142 normal meter of hydrogen per hour per every hour, then it shows that an electrolyzer, which actually produces hydrogen with a capacity of at least 600 megawatt, is required to generate that amount of hydrogen. That is major thing. That is the engineering thing. That's a major thing. The second point is that sourcing of high grade iron. Actually, in this process, high grade iron is required. The more purified iron ore. Okay. Actually, this the grade of iron ore, the grade of iron ore is basically depicted by the percentage of iron in that iron ore. Okay. Say for example, in an iron ore, there is 65 to 66% is iron, and the rest is of impurity like sulfur, silicon dioxide, silica, calcium, lime, all those things are there. So impurities are there. So this process, this hydrogen-based process, it needs high grade of iron ore. At least 65 to 70% of iron should have to be there. But what is happening? The low quality of iron ore is actually being available in the market, in the globally. In most of the mines which are producing iron ore, we are seeing that their iron percentage is gradually declining. Almost 4% of iron ore has been declined in the Australian mines, right? So low quality of iron ore will lead to increased gangue material. Now, say I'm giving an example. In an iron ore, as I said, the 70% is the iron and the rest is the impurity. Now, if you get the low quality of iron ore, then probably 60% of the iron and the rest is the 40% is the impurity. Now, if the impurity is more, then you have to have that impurity. We have to have the reduce this impurity or remove this impurity through the beneficiation, like crushing, milling, separation, and more mining of ore is needed. Okay, so this is a issue and problem for the hydrogen-based DRI, because hydrogen-based DRI effectively work if it is a high grade ore. Okay. The third one is that in the last slide I had shown, that is the endothermic. So it needs heat, it needs energy. If it is endothermic, then it cannot produce that much of iron as the BF and BOF produces. So achieving a good heat energy balance due to the endothermic nature of hydrogen in the UF is a challenge. This also suggests that hydrogen gas entering the layering furnace must be preheated, okay, to ensure a heat balance. It must be preheated. Okay, so it is an endothermic. So in order to overcome that endothermic atmosphere, there's some sensible heat should have to be put to the hydrogen, and then it will be pushed into the direct reduction furnace. So that you are supplying additional energy, heat energy to the hydrogen DRI, which was not required in the coal gas system because their reactions are exothermic. Automatically their temperature goes up, right? The other important point, this is also very important, that before I get into it, I just want to explain that that iron, the liquid iron, uh, is on top of it, the slag floats. Slag is the impurity. Gang, slag. The slag floats on top of the liquid iron. Okay. But they are separable. They are basically they are different. Something like that. The milk and the crust of the milk. So in the crust of the milk, you just simply put a spoon and then separate it out from the milk. So it is easily separable. So there's no problem with that when it is in the main route of the BF-BOF route or the DRI-UF route where coal is charged. Coal and coke, carbon is charged. But that is not happening with the hydrogen. The characteristics of the slag, that's change because of this hydrogen-based extraction. What happens that the slag gets dissolved in the iron. So it's very difficult to remove the slag impurities from the iron itself, right? So it is saying that removing and controlling impurities like hydrogen, sulfur, phosphorus is challenging due to the non-foamy slag. The slag is not slag. Basically, it is not separable. It remains. It's included in the hot metal itself. So due to the absence of carbon, and the carbon actually does a lot of things. Carbon, it's a reducing agent. Carbon, it is an exothermic reaction. It gives heat to the furnace. It reduces that extracted iron from the oxide. And also carbon, it starts, carbon itself, the carbon dioxide, it starts the molten metal. Like if you start the milk, that uniformity will be there. So it starts, but in hydrogen doesn't do it. So carbon, it starts. So as it says that due to the absence of carbon, there will be yield loss. And unless substantial carbon is added to the system. So you have to add some carbon to start it, which again increases carbon dioxide emission. Okay. So zero carbon hydrogen DRI manufactured with low grade ore may negate the benefit of the using hydrogen. Therefore, the production of steel using hydrogen makes the process difficult to balance the carbon content and energy consumption. Okay. So hydrogen is good for not emitting the carbon dioxide. That is true. And hydrogen is a very good reducer agent, very good reducing. Its reducing efficiency is better than the carbon itself in many cases. But the other thing is that it's endothermic, so it cools down it cools down, and so it's needed preheat. It needed energy supply from the outside. And also some characteristics of the slags impurities that dissolves, they are not foamy, so it is very difficult to separate out the slags from them. It's a challenge. And in order to do it, you have to add carbon. And again, then what happens? You are adding carbon, you are adding heat, adding energy, and just to reduce the carbon dioxide. But again, it's negates the benefit. Okay, so these are the challenges. These are the challenges for the futures. I'm showing some microstructure growth when hydrogen is being used, and you see that the microstructure are of the different temperature, 600, 800, 900. Actually, this doesn't happen with the carbon. Carbon, the microstructure at the 600 level to 800 level to 900 are more or less the same. That doesn't change. Okay. But if you use hydrogen, then the microstructure changes. The problem is that if you increase the temperature, I don't want to get more into it, but if you increase the temperature, then you'll find the sintering, that you will find that porosity of the iron ore reduces. What happens if the porosity of the iron ore reduces? That the gas, like the carbon gas or the hydrogen gas, cannot go inside it, and so cannot diffuse inside it. And if it can't diffuse inside it, it cannot react with that iron inside. So if you can't react with the iron inside, then you are not extracting the iron. So the process will be slower and slower. Okay, so this is what is happening with the temperature. This is another very challenging part. If pure hydrogen is being used. The other method I'm coming from I have already discussed about that hydrogen-based DRI-EAF process. Now there is another process which I'll not discuss. Probably there's one subject which has been taught to you or which has been discussed in a lecture sometime back. It is the CCUS, carbon capture, CCUS. So CCUS involves capturing carbon dioxide emission from steel plants for either storage underground or utilization in product. Potential capture points include blast furnace gas and off gas. So whatever gas which are coming out from the blast furnace, if there's a process, they can be stored underground. Just simply they are stored, just sequestered. The captured CO2 can be sequestered geologically or converted into useful chemicals such as ethanol or by microbes. Okay, so this CCUS could theoretically retrofit existing assets. Its full commercial implementation blast furnace is still in early stages. As of 2024, 6 steel plant CCUS projects are in development, but progress remains slower than hydrogen-based route. So this is another route. What they're saying, the scientists are saying that better capture the carbon dioxide which is getting emitted from the blast furnace at the source, at the top, and then put it into the it's just simply sequestered, put it in underground or some storage area, underground, and put it in some storage area and keep it over there, like the CO2 is being stored over there. Or else the CO2 can be converted into the ethanol or some other chemicals by microbes. So this is the basically another strategy of getting the CO2, or basically the CO2 which is being emitted, it's not going into the atmosphere, they are being stored in the underground. But this is a huge infrastructure things to be developed. And as I said, that 2024, some of the companies, they have started using it or they are experimenting it, and the results are still not being published. The another method is this is another method is electrolysis, and this electrolysis is an advantage is that it's a no direct CO2 emission, modular potential, utilizes low grade or fine ore. It's unlike the H2 DRI, it can use low grade and fine ore, pure oxygen byproduct for industrial uses. The Boston Metals aims for demonstration plant by 2020. Challenges include very high power consumption, material engineering for corrosive molten oxide environments, and scaling from pilot to industrial. Electrolysis could be a leapfrog technology for 2040 and beyond, offering a long-term research frontier for academia. Actually, this is still in the laboratory regime. This is still under experimentation regime, and I'll just explain what is that electrolysis process in a brief. But it is not yet been commercialized, but it has a potential. And as I said, that the target of scientists, the 2040, 2050, where the electrolysis process will come in place, which will replace that BF-BOF route, and this electrolysis process will produce steel. Okay, what is that? Basically, what we are doing, there's an iron oxide, which is iron oxide is nothing but the iron ore. So iron ore is available in the planet. So you have to mine that iron ore. Now you have to process the iron ore to extract the iron from the iron ore. That exactly is what we have been doing it, or I've been telling you. The first process is the BF-BOF route. You extract the iron from the iron ore by inserting the carbon gas or the coal gas or the coke, which burns inside, and then this carbon monoxide, it extracts, it's a reducing agent, it extracts the iron from the iron oxide and then produce the liquid pig iron. This pig iron then goes to the steel plant, and then in the steel plant, it's a basic oxygen plant. It's lances insert push highly purified oxygen, which oxidizes all the impurities like the carbon to carbon dioxide, sulfur to sulfur dioxide, phosphorus to phosphorus oxide, K2O. Okay, and then the residual is a free of impurities. It's becoming a steel. Okay, that is the process. So what we learned that the first one is the BF-BOF route, which is a 75% of the steel plant. They use this one. It's a huge and massive, and but it emits lot of carbon dioxide, 1.2 million tons of 1.2 tons of carbon dioxide per tons of steel. Then that EAF route and DRI EAF route. This is a 25% the steel plant uses it, and the carbon dioxide emission is lesser, very less compared to the BF-BOF route. Then comes that how is it possible to replace that the coal gas by the hydrogen? So it comes a hydrogen DRI. So instead of coal gas, they replace the hydrogen DRI, completely hydrogen. Now, why hydrogen? Hydrogen is also a reducing agent, like the carbon monoxide, like the coal. Okay, it's a very good reducing agent. And the other point is that when the coal is used, it emits or it creates, it develops carbon dioxide. But when hydrogen is used, it develops steam, iron and steam. So steam is harmless and useful, whereas carbon dioxide is a waste. Okay.
गुरु ने भी मेरी चीटिंग करने में हेल्प करी है। 30 क्वेश्चंस आएंगे, फटाफट उसके आंसर ढूंढने हैं।
Okay, then yeah, may I proceed? Fine. Now these are the some schematic diagram of the electrolysis process, and here the anodes and cathode are being used to just to separate iron from the cold iron ore. There are different type of electrolysis process. I'm not going into the details. The time is not much, I think. There's one is that hydrogen plasma smelting reduction, then the alkaline iron electrolysis process, then molten oxide electrolysis process. And what I want to mean here, I just want to go to the I want to touch the key points. The first point is that the process has a carbon dioxide reduction by 87 to 95%. This is the one key point. And the second is that you can see the equation here, that half Fe2O3, it is by the electrolysis method, it is just simply separating Fe and O2. So Fe is the iron which we need for the steel making. Okay. What are the challenges? Challenges is there's a very high heat loss. If you go to the electricity, very high heat loss, 40% of the heat goes waste. Very low current efficiency and the corrosiveness of the electrolyte. The electrolyte becomes corrosive. After some use, you have to throw away the electrolyte and you have to replace a new electrolyte. So as of now, this process is not yet economically feasible, particularly due to the unavailability of the carbon-free cheap anode capable of sustaining a corrosive environment. So the corrosion takes place in the electrolytes. That is the challenging, and it's a very high heat loss is there. But it is having a potential because it reduces almost 87 to 95% of the carbon dioxide. Okay. The process is that iron ore is first grounded to about 10 micrometer range, and then it is put into the molten bath, and this electrolysis, the cathode and anode, is being pushed in the molten bath, where iron is separated from the oxygen. There's another process method is there, that is the biomass. So as of now, I have said that hydrogen DRI, and I also explained about that carbon dioxide CCUS, that's carbon capture, what we say, and which is sequestered, and then that is the way, one of the way of reducing the carbon dioxide from the atmosphere. The third is the electrolysis process, which is just simply it is under the experimentation now, and people are thinking that after 20 to 30 years after, the electrolysis process may come up in a big way. There is a biomass method is there. This biomass method is what is actually happening. It is basically the same DRI process where pure hydrogen is not being used. The coal gas is being used with the hydrogen. So some processes are there. This is one of the process where the ore is first, the main ore is first ground into small particles, and then it is preheated. And it's preheated to around 700 degrees centigrade, and it is first being reduced in a cyclotron, and then it is put into the smelting region, smelt reduction vessel, where the dry coal is being used in the smelter, and in this smelter, that the iron ore, the small particles of iron ore are reduced to iron, hot metal. So this is the process, and here is also that oxygen and the hydrogen is also being used, and coal just to replace a little bit of the coal from it. So this is one process. This the process Hisama is a coal-based iron making technology which I had just shown. It is being developed by Tata Steel, which is a combination of cyclone converter furnace and smelting reduction furnace. It targets to reduce carbon dioxide by 80 to 95% by 2050. It is a direct smelting process based on coal-derived biogas. In this process, iron ore particles are preheated and pre-reduced in circulating fluidized bed reactors integrated with two-stage cyclones. After that, the hot ore is transferred to a smelter to produce liquid iron. In this process, coal-derived biogas can be replaced by renewable hydrogen fully or partially. This is another process. This is a Codex process and the Phoenix process. The Codex process is a smelting reduction process that produces iron directly from iron ore and non-coking coal. This process combines a reduction shaft and melting disappear. Similar to the previous one. Same thing. Iron ore is in the form of lump, pellets, and sinter is reduced in the reduction of shaft and forms DRI, which is then transferred to the melting gasifier smelter, where non-coking coal is injected as a source of energy and reductant. The coal-derived reductant consists of mainly hydrogen and carbon monoxide. From the melting gasifier, it's cooled and cleaned before injecting into the reduction shaft. The Phoenix process is similar. These are the similar type of process. What is happening that the iron ore is first being crushed to small particles, and then this iron ore are partly reduced. Partly like the iron. What is the iron ore composition? Is Fe2O3, hematite, Fe2O3. It is reduced to woodstad, FeO. They are reduced in different in a fluidized bed burner, a boiler, or they are reduced in the cyclotron in different areas. They are reduced by the coal gas. So Fe2O3 reduced to FeO in the cyclotron. These are teeny particles, and they are preheated particles, iron ore particles. Okay. Similarly, in the reactors, they are all reduced, and they are reduced to FeO. This FeO now goes to the smelter, the melting gasifier. It is now melted by the electrodes, high temperature molten bath, and the coal and hydrogen is injected in the molten bath, and it extracts the iron from that FeO, woodstite, and the carbon dioxide and steam, with the mixture of the carbon dioxide and steam, that it's liberated and that goes to the atmosphere. So, so you can ask that here is the carbon dioxide is also being emitted. Actually, this coal gas can be replaced by the hydrogen gas. That is the beauty. So as of now, they are using coal gas. What is happening? They are not taking the risk of replacing the entirely coal gas by the hydrogen, because the renewable energy is not there. The converter, the electrolyzer are not there to produce so much of hydrogen. So what the people are doing, they are mixing that coal gas with that hydrogen, whatever hydrogen they get. Okay. So what the output is that carbon dioxide as well as the steam, and there's a iron, molten iron, which is coming out from the molten bath, which goes to the steel plant and get converted in electric arc furnace to steel. So the process is that Codex, Phoenix, and the previous one is that Hisama, Codex, Phoenix, and there are many Midrex. Lot of trials are being taken. Codex, Phoenix, Hisama, Harshna. So all of the principle is the same. The principle is that get the iron ore from the mines, crush it into minute particles like 10 micrometer, and then preheat it in the cyclotron or in the fluidized bed, and preheat with the coal gas itself. Preheat with the coal gas, preheat and reduce it by the coal gas. What is happening that, as I said, the iron ore particle is a hematite or magnesite, and the formula is Fe2O3 or Fe3O4, higher oxides. It is reduced to the lower oxide, that woodstite, which is the FeO. So now this FeO, which is formed from the minor particles, it goes to the molten bath, that is smelter, and with the electric arc, this molten bath is having a very high temperature, and it's becoming liquid. It's a bath, it's a liquid pool of FeO. Now you are charging the coal gas along with the hydrogen gas to the molten bath. This bubbles out, and then they reduce that FeO at that high temperature to Fe, and they themselves get converted to CO2, carbon dioxide, and hydrogen steam. So carbon dioxide and hydrogen, they emits to the atmosphere. I have talked of the Codex, Phoenix, and I skip this one. Now I'm come to the end of the my lectures. The innovations in energy efficiency and other enable tech. Uh, I, I'm keeping this slide because that other than these processes, there are other ways of reduce of other ways can be applied to reduce the carbon dioxide, reduce that climate pollutions. The other ways are like the AI, artificial intelligence, for process optimization to minimize energy waste, reducing digitalization, industry 4 tools, IoT sensors, digital twins, AI and ML, optimize processes, detect inefficiencies and manage energy incentives, electrification and ancillaries, replacing diesel equipment with electric using something, emerging ideas, research into direct electrochemical iron reduction at low temperature, like the microwave plasma-based reduction, alternate reductants like green ammonia or biomethane. These are the emerging areas. So it is not confined to the hydrogen. It is not confined to the electrolysis. It is not confined to the coal and hydrogen mixed gases like Phoenix and Corex. But in future, it can be the other reductants like ammonia, green ammonia may come in, biomethane may come in. These are all reductants. Not only that, along with this, the today's world, which is basically working on the AI system, ML system, machine learning, artificial intelligence, digitalization. These also will help to reduce the carbon dioxide emission. This is a separate chapter that can be discussed later, but there's a possibility of reduction of carbon dioxide by using this point. So coming to what I said is the other than the standard conventional and traditional routes like BF, BOF, blast furnace and basic oxygen furnace, and which is 75% of the steel making steel plants uses it, and which produces 1200 kgs of carbon dioxide to produce 1 ton of hot metal. And the other route is that DRI and direct reduction index iron and EAF, that is electric arc furnace, which direct reduction iron is producing the pig iron. I have shown the picture, the pig irons and the briquettes, which is used in the electric arc furnace, where the electrodes are being pushed to convert in the electric in the molten bath, and oxygen is launched to get rid of the slags or oxidize all the impurities. Like the carbon is converted to carbon dioxide, sulfur is converted into sulfur dioxide, phosphorus is converted into K2O, phosphorus oxide, amino oxides. So all oxides are being formed, and the carbon dioxide is a gas which escapes. The others are solids which remains as a slag and floats on top of the steel, and they are gradually taken out and the steel is poured out. Now comes that how to reduce that carbon dioxide. So the scientist says that why not use hydrogen, because hydrogen is an excellent reducing agent. Number one, but excellent reducing agent. And on the other, the benefit is that when you are using carbon as a reducing agent, you are getting the carbon dioxide as a byproduct. But when you are using hydrogen as a reducing agent, you are getting steam as a byproduct. So which is a very beneficial. But there is also some challenges. The challenges are what? One is that getting that hydrogen, producing hydrogen, so much of hydrogen is a challenge. The electrolysis process are not much there, and it's pretty expensive now. Second is 600 megawatts of electrolysis process is needed to produce 14 tons of hydrogen per hour. So it is important, 12 tons of hydrogen per hour. So it is important to have a better electrolysis process. Second thing is that hydrogen is, unlike the carbon, hydrogen is endothermic, so it cools down. Endothermic is it absorbs the heat from the atmosphere, from the environment, so it cools down. So you have to supply energy, heat energy from the outside. So there is an additional heat energy from the outside. Third is that important point is the slag. The slag in the carbon atmosphere, the slag floats on the hot metal, and they are separable. That they can separate the slag from the hot metal easily. But in the hydrogen, the slags are not foamy. They may get dissolved into the hot metal itself, the slag. So it is very difficult to separate the slag from the hot metal. Then comes the CCUS. CCUS is not being touched in this lecture. It's nothing but whatever gas which are being omitted from the blast furnace or BOF or DRI, before they enter the atmosphere environment, they are captured. They are captured by some methods, and they are captured, and then they are sequestered underground. They are stored in underground, or they are converted in ethanol using microbes. Then comes the electrolysis process. Electrolysis process is simply that there is a molten bath, and the electrodes are being used, anode and cathode, and through the electrolysis, that iron is extracted from the iron oxide directly, and the oxygen goes to the anode, and iron goes to the cathode. Then the biomass and renewables, these are the common thing. Many people are using, like the Codex method, Finex method, Finman method, Hispan method, where the iron ore which are mined, they are first crushed into a very low. They're crushed to the micro level in microparticles, and through cyclotron or through the fluidized beds, they are preheated and they are partly reduced, and then they are put into the smelter in a molten bath, where coal gas and hydrogen and methane gas are injected, and there's a reduction take place in the bath, and iron are separated, and again the carbon dioxide and steam or hydrogen oxide, they are produced, and they are basically emitted to the atmosphere. The process I have already described, so I'm coming to the last part of my session. It's just to give some information that what is happening all over the world regarding the green steel. So I just read out here: EU, European Union, Green Deal targets net zero by 2050. 55% reduction by 2030. That's the target. EU emissions trading system. Steel plant must buy carbon dioxide permits. Carbon border adjustment mechanism. Tariff on imported steel CO2. We know, as of now, we are knowing a lot of things about the tariff. So tariff may be considered on the steels which produces the CO2. More CO2 they produces, more tariff will be imposed on them. Clean steel partnership. Clean steel partnership here is important for the academician. That millions of R&D for hydrogen CCU technology are being floated. The universities are being asked to do the research. Then 40 gigawatt electrolyzer target by 2030. Electrolyzer means that electrolysis of the furnace. Then Europe leads to it hydrogen DRI pilots, CCUs, and public green procurement. These are the policies which I just read. Global climate COP26 Glasgow breakthrough on steel, which I already said. Near zero steel again preferred by 2030. India places low carbon steel in government projects. China to peak steel emissions before 2030. Expands EF route. US first movers coalition launched at 2020 at COP26 to boost green steel demand. Talks for global clean steel standard and US-EU low carbon trade. International knowledge sharing. Japan, Canada on CCU's H2. So all people all around the globe, they are now talking about this hydrogen-based DRI, talking about the electrolysis, talking about this FinMex and Corex systems, and they want to replace that BOF route. They want to replace the DRI-EF route. DRI-EF route will be there. Only the carbon monoxide, that's coal gas will be replaced by the hydrogen. So more DRI and EF route, less BAF and BOF route. And by 2050, you will not find, will not be there. I'll not be there. There will be no BOF route in 2050. Okay. So same thing. IRA 2022 incentives for clean industrial technology, key for green steel. Then $3 per kg hydrogen production credit. So if you produce steel using hydrogen, then you will get a credit from the bank, from the government. $3 per kg. $85 per ton of carbon capture. Grants for iron making smarter EAF, clean technology pilots, buy clean policy mandates, low CO2. Who are the industrial leaders now who are doing these things? SSAB, hybrid SSAB, LKB, Vattenfall. They delivered fossil-free steel to Volvo 2021, prototype car in 2022. So the Volvo prototype car in 2022 is being produced, is being developed by a steel which is a fossil-free, means which has been produced via the hydrogen route. They are building 500 megawatt electrolyzer to large-scale hydrogen production. 10% of Sweden's emission to be cut via SSAB transition, SSAB hybrid. Academic collaboration with KTH, Lucia University for R&D. I finish over here. Nothing to say more about it. It's all. It's like the case study of the ArcelorMittal. They vowed and promised to reduce the carbon dioxide by 2030. CCUs, they will use CCUs, H2 DRI plant in Canada, Spain, hydrogen switch plant, grid steel certificate. Yeah, I think has spoken. I've given that, delivered my lecture on the steel, the near future steel, the clean, the green, and near future steel. And mainly it's saying about that hydrogen-based steel production, not the carbon-based steel production. It is talking about that electrolysis, direct electrolysis of the iron ore, where extracting that iron from the electrolysis process via electrolysis process. Is saying that CCU, which is capturing the carbon dioxide. Even if you omit the carbon dioxide in the atmosphere environment, before it goes to the environment, it's being captured and put it in underground. And this carbon dioxide is converted into ethanol and some other things. And I also touched about that Phoenix and Codex process, where in the smelter, coal gas is used and hydrogen is used to get extracted iron. This is done. Any questions?
Hello, sir.
Yes.
Myself, Dr. Mane, is there any guideline for the industrial steel making in India for zero carbon emission by government of India?
JSW and Tata Steel. Tata Steel, they have the plant in Europe, and they are doing an experiment over there in Europe, Netherlands, which I also mentioned over there. That is a Hisana process. And I personally have visited that plant. I have seen it. So it is still under experimentation. They have a lot of problems and issues, but it's a research work. It is experimentation work. A lot of money are being put into it. So as of now, the JSW and the Tata Steel, they are looking forward. They have to go for this hydrogen-based steel. They have to reduce the carbon dioxide, because one of the reason is that properly. We are coming to the. Just a minute. Can you give me a minute? Second. I have to take a little bit of water. So all of you are now hearing here and there in the TV the tariff, US tariff. Now Tata Steel, JSW, and many steel plants, they also export steel to the USA, right, from India. Now, if there could be a case that they might say that that there will be a carbon credit or carbon discredit, which means they also measure that how much carbon dioxide you are producing from your steel plant per ton of steel. Okay, if it is 1,000 kg per ton of steel plant, then your tariff is this. That means we have to buy the steel. You are discredited. You are discredited of this, and then we have to buy the steel, or you have to give it in discount, something like that. You have to lose your money. You have to lose your money. Okay, so that stringent laws are coming globally. We all know about the Delhi. It's a highly polluted city. So we have to think of it. As I'm just giving the answer, that JSW and Tata Steel, they are in advance. And the government itself also, they are planning it, they are looking for it, they are thinking of it. And as I can say that you people, the academics people, you must take up the projects, must take up the R&D projects regarding this climate CO2 emission, reduction of CO2 emission. There are so many things are there. You can make a prototype over or in the Attitude Institute and do and make some demonstration, do some jobs. Any other question? Any other question?
Yeah. We sincerely thank Mr. Abhik Roy Chowdhury, sir, for his inspiring and insightful lecture on the green, clean, and future steel. Today, during his lecture, he has defined what is clean and green steel, why it is a subject of concern. He also has explained about various impacts and co-benefits of green steel, various emerging technologies of green steel, opportunities and challenges involving it. His pioneer contribution and innovative vision has provided us with deep knowledge and motivation to work towards sustainable solution. Thank you, sir.